Okay, hello, my name is Lilith, and I'm one of your TAs for this quarter's or this summer's BIBC 102. And I'm just doing a quick video going over problem set 2 about the answers that we talked about in class, and also maybe just give you a little detailed explanations on them in case you need it. So let's first start with question number 2, because if we draw out number 2, number 1 would be much easier to answer. I'll go ahead and skip number 3 because it's more of an answer that you need to give about what you think enzymes do, and then we'll go over number 4 and then number 5. Okay, so for number 2, it's asking us to draw a reaction coordinate diagram or an energy diagram that shows an exergonic reaction under standard conditions, and it asks us to make sure we label these 4 bullet points on this diagram. So let's go ahead and do that. If you remember, I'm going to zoom in here. An energy diagram is going to consist of a y-axis and then an x-axis. Our x-axis will be reaction coordinate, just meaning, the path of the reaction or the progression of the reaction. And our y-axis is going to be free energy. We can say free E. And in this case, we are asked to draw an exergonic reaction, right? Meaning that our delta G prime naught is going to be negative for an exergonic reaction. And for us to obtain that on a diagram, we're going to draw one where the substrate, which is where we start the reaction from, ends up being higher than the product ground state. So substrate going up, the activation energy to the transition state, and all the way down to the product. And this is where our product ground state would be. This is our transition state, T for transition state. Now, the energy that is needed to overcome this energy hill and to get to the transition state is called the activation energy, or delta G double dagger. So, just on the side for you to know, activation energy is the same thing as delta G double dagger. So let's go ahead and draw that in. I'll do it with purple. So going from this energy state to the transition energy state is the activation energy. Oops, I need a pen for that. Is the activation energy. That was horrible. Hold on, I need to do that again. The activation energy for the forward reaction, right? So if reaction is going substrate to product, this is the amount of energy they need to get the substrate activated, in a sense. Okay, so this will be the activation energy of substrate to product. Now, what if we were looking at this reaction going backwards, the reverse version of this reaction, where this was our starting material and this was our ending material? Then we would start here, we would have to go through a higher activation energy, then come out here and end over here. Now, this reverse reaction that I just showed you is endergonic, because where we end up is a higher energy level than where we started. Okay? However, this reaction has an activation energy as well. It's just a lot larger. That's why it's a lot less attainable. So let me change my colors here to red. And let's show the activation energy needed to go from the product to the substrate. That's how big it is. So that's the activation energy of product to substrate. Once again, it takes a bigger hill, a bigger energy hill to go this way than to go this way. That is why substrate to product is going to be a more favorable and attainable reaction. Okay. Now, we have the two activation energies down. It asks us over here, S to P, P to S. Now it's asking us, what is the activation energy, or delta G double dagger, with the addition of an enzyme catalyst? So if there is an enzyme that is trying to help this reaction, either going from substrate to product or the reverse direction, the enzyme is going to stabilize the transition state, okay? And it will do so by reducing the activation energies needed to perform this reaction. So if there is an enzyme involved, and here I will pick the green color, so I'm going to write plus enzyme. So green is when there is an enzyme. Then the graph would look like this. It would look about like this, right? So the activation energies of both the forward reaction and the reverse reaction would be decreased, and they would be decreased to the same extent. Now, this does not change the thermodynamics of the reaction because, as you can see, this green reaction with the enzyme is still exergonic, and this reaction, the reverse reaction, is still endergonic, and that is because the enzyme does not change the free energies of the substrate and the product. All it does is it changes, and it reduces, to be more exact, the activation energies of the forward and reverse reactions to the same extent. Okay? Because of this, the reaction will now be faster. That is why we are talking about kinetics, right? It's going to be faster. But the concentrations of products and substrates under standard conditions will not change because the enzyme does not change delta G prime naught. It does not change it. Okay? And the last thing that this question is asking us to note is the delta G prime naught of the reaction. And delta, as some of you may know, the term delta is change, right? It equals change. So change in G prime naught, so change in energies. So all you want to do is see where the energy level of substrate and product are, and you just take the difference of those. So we will take the color blue, and we'll do this. So wherever the substrate is, wherever the product is, the difference of that is delta G prime naught. And there you go. That is basically all you need to know, I think, on the energy diagram, and definitely all you need to answer question number 2. Now that we've drawn this whole thing out, we can go back to question number 1 and answer that a lot easily. So which of the following is caused by enzyme catalysis? If you haven't done this problem set yet, I would advise you to stop this and just think about it by yourself from all that we discussed here. But if you already have the answers, then let's go over them. So the 3 things that the enzyme would do, at least within this question, is to increase the forward reaction rate. And let me draw that in. We'll go with pink. So it will increase the forward reaction rate by reducing the activation energy. It will also increase the reverse reaction rate, again, by reducing the activation energy. And exactly what I just said. It will decrease the delta G double dagger, which is, as you remember, the same thing as activation energy. So those are the 3 answers for question number 1. Okay, question number 3, it's just asking you what enzymes do in your own words, how they affect catalysis, how they affect kinetics, how they affect thermodynamics. So make sure you write something that is not using as much jargon, but just layman terms, explaining what enzymes do as if you would explain it to, let's say, a 10-year-old. And that exercise will really help you have a deeper understanding of what enzymes are and what they do to reactions. Question number 4, this one is a little bit of calculation, so let's take a look. So an enzyme obeys Michaelis-Menten kinetics, and it has a Km of 25 micromolar. Use Michaelis-Menten equation to determine the percent of Vmax of the enzyme at the following concentrations. Now let's break down this question a little bit. So when we talk about Michaelis-Menten kinetics, and I have a separate video on this, so if you like more information on this, definitely watch that. But I can go ahead and talk about it a little bit here. Let's go ahead and draw the diagram where we talk about Michaelis-Menten kinetics and reactions that follow Michaelis-Menten rules. Okay, and this is for number 4. So the graph that we're going to draw right now is the Michaelis-Menten kinetics graph, where the x-axis is concentration, and if you don't know, bars like this or parentheses like these mean concentration, so the amount of something. So the x-axis is concentration of substrate present within the reaction, and the y-axis is velocity of the reaction, so how fast the reaction is going, or the rate of the reaction, all same thing. At the very top of the y-axis, we have 100% velocity, otherwise known as Vmax, so maximum velocity possible. If this is 100%, then hopefully you understand that half of it is 50% of Vmax, but we like to call it 1/2 Vmax. 1/2, 50%, same thing. And every other point on this y-axis is going to be some type of velocity, which we will denote as V0. Okay, so anything, any point, or any value on the y-axis is going to be some velocity that we can call V0, or we can express the value, any value on the y-axis, as a percent of the total Vmax. So if this is 1/2 Vmax, then somewhere here we will have 3/4 of Vmax, and somewhere over here we will have 1/4 of Vmax. Okay, or we can say that in percentages. We'll say 25% Vmax here and 75% Vmax over here. So hopefully that makes sense. And now looking back at the x-axis, every single value on the x-axis is going to be a concentration of substrate. So maybe over here we have 100 micromolar, and over here we have 10 micromolar. Maybe we're not counting our substrate in micromolar, we're counting it in molar. Let's say here we have 100 molar, which is very, very concentrated, and here we have 10 molar, or we can do millimolar. It doesn't matter, as long as it's a concentration. And the farther we move to the right, the concentration will increase. So in general, enzymes that follow Michaelis-Menten kinetics, they will show a reaction coordinate that looks something like this. Let me pick a purple color. It will look like this. It will start off going super high, and then it will plateau at some point. And any reaction that we take a look at will be a variety of this one, right? Not all of them look like this, but let's just say the one that we're looking at looks like this. Now, let's say we would like to find out the Km of this enzyme. What is the Km? How do we know that? Well, Km is the concentration of substrate, so it is a value on the x-axis that shows us when the enzyme will work at half of its maximum velocity. Once again, Km is a concentration of substrate. So Km is a point on the x-axis, somewhere on the x-axis, that will show us where on this graph 1/2 Vmax is attained. Okay, so let's take this graph specifically and let's find the Km, and I will use a green color. So first we want to find 1/2 Vmax, it's over here, and we want to go to the graph. So dot 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 to the graph, okay, and then we're going to come down to see at which substrate concentration this is, and boom, this point right here on the x-axis that shows us concentration of substrate tells us that this value is Km. Now we found Km for this specific enzyme. Km is an intrinsic factor of the enzyme, meaning that only this enzyme has this Km for its specific substrate. Okay, and we as scientists in the lab, we cannot change the Km of this enzyme unless we go and physically modify the enzyme, right, or engineer the enzyme. So Km is something that is just dependent on the enzyme, and more specifically the active site of the enzyme. Okay, so Km is something that identifies how strongly the enzyme has attraction to its substrate. So let's say we have an enzyme, it has this little active site triangle, and its substrate is going to look just like the active site, and it's going to want to go and get tucked into this active site, nice and firm. Now, the tendency of this enzyme to want to take the substrate and put it in the active site and perform the reaction, the tendency of that, or the attraction of this enzyme to this substrate, is called affinity. Affinity. And affinity is shown by the Km value. Why is that? Because Km tells us how much substrate is needed to get to as much as 1/2 of Vmax for this enzyme to work 50% of its maximum velocity. Now let's think about it. If this enzyme needed a lot of substrate, let's say where's my blue marker? Let's say there needs to be so many more of these. Let's say there's 100 times 1,000. There needs to be 1,000 of substrates for this enzyme to finally attract one and perform a reaction at 50% of its speed. The Km for this enzyme is very, very high because you need so much substrate for this enzyme to get to 50% of its Vmax. But if this enzyme only needed a few substrates, so let's say only 3 times 10, only a few enzymes to work up to 50% of its Vmax, then its Km is pretty low because it doesn't need as much substrate. Now let's take a look at that same topic on this graph. So right now we have an enzyme kinetics graph that shows a Km that resides over here. So in the grand scheme of things, in the grand scheme of this x-axis, this Km seems pretty low, right? It's a small number. Let's say it is, let's give it numbers. Let's say it's 10, then we have 20, then we have 30, 40, 50, and we'll call it micromolar. Now, this tells us that this enzyme needs only 10 micromolar substrate for this enzyme to work at 50% of its maximum velocity. Now, if there is another enzyme that has kinetics graph like this one, for example, let's take a look at its Km. Its Km is going to be, a lot bigger, twice as much, right? So this enzyme is going to need twice as much substrate to work at 50% of its Vmax. So this enzyme, even though it has a large Km, meaning that it needs a lot of substrate, it means that it doesn't have high affinity for its substrates because it needs so much of it. Whereas this one needs only a little bit to work at the same 1/2 Vmax. Whereas this one needs twice as much substrate to work at 50% of Vmax, meaning that this red enzyme has low affinity for its substrate. So from this, we can deduce a simple, memorization statement that high Km equals low affinity and low Km equals high affinity. But I strongly recommend that you actually understand the idea behind this, because only memorizing this will probably not serve you too much for this class and for future classes or for studying for the MCAT. So definitely try to understand this, and if you have any questions, let me know or let other TAs know, and we will try to help you. Okay? So, went a little too deep with these kinetics, but basically this is Michaelis-Menten kinetics. Okay, and let's get back to question 4, because that is why we drew all of this, to kind of explain what's about to happen in question 4. Now, another thing you want to remember for question 4 specifically is the Michaelis-Menten equation, and you don't have to remember it, you just have to know it, and the equation goes like this. V naught equals big parentheses, substrate concentration over substrate concentration plus Km times Vmax. Now let's unpack this equation a little bit. This basically is telling us that V naught, which is just some rate number or velocity number on the y-axis, V naught is some fraction of V max. Once again, V naught, which is any number here, is some fraction of Vmax, which we already covered, right? So 1/2 of Vmax is just another number, right? It's just another V naught. If we were here, the V naught would equal 1/4 Vmax. So V naught is just a fraction of Vmax. So if the question asks you that Km is 25 micromolar, so we can plug in Km over here, and it tells you exact concentrations for different scenarios, it's giving us 5 scenarios, concentrations of substrate, then let's take this first scenario. Let's solve this one. So substrate is 5 micromolar, and we can substitute it here and here. The answer would be V naught equals, big parenthesis, 5 over 5 plus 25, okay, times Vmax. And guess what we get? We get V naught equals some fraction of Vmax. And that fraction in this case is 5/30 times Vmax, which is the same thing as 1/6 times Vmax. So V naught is just another number on the y-axis, and it is a fraction of the total Vmax. Now here it's asking you for percentage, not fraction, so all you want to do is actually take a calculator, do 1 divided by 6. I think it turns out to be 0.166 or something, and you round that to 0.17, which is 0.17 times 100 to make it into percentage, 17%. So the answer to this one would be 17%. Okay, so that is how you do it. I believe the answer to the second one is 38, and I will leave the rest for you to do using the same equation. All you have to do is plug in substrates, then Km, find a fraction of the Vmax. Understand that a fraction of the Vmax is just some value on the y-axis, and just turn that fraction into percentage because that is what the question asks you for. Okay, very good. So done with question 4, and let's quickly talk about question 5. This video is getting longer than I wanted. Question 5 is asking, with a little bit jargon, compare the enzyme from question 4, so the enzyme that has a Km of 25 micromolar, with one that has the same Vmax, but a Km of 0.5 micromolar. Great. So we are comparing an enzyme that has a Km of 25 micromolar and an enzyme that has a Km of a much, much smaller number, 0.0 micromolar. I will zoom in here and draw another diagram so that we can compare these two. Okay, so first we have one that has a Km of, whoops, that was bad. First we have a Km of 25. So if this is 1/2 Vmax, we try to find its Km. We said one of them is 25. So that's the Km of the first one. And now let's take a look at the second one. The second one is going to have a smaller Km, so my graph needs to be a lot steeper, and they have the same Vmax, right? Same Vmax. And the Km in this case would be down here, and this graph that I just drew is not proportional whatsoever, but let's just say that is 0.5 micromolar. Okay, now the question is, after we draw this out, Km of 25 and Km of 0.5, exact numbers are not necessary. Aim to explain the functional difference of these two enzymes as substrate concentration vary between 15 and 40. So it's asking us to take a look at how this enzyme would work if concentrations of substrate varied between 15 and 40. Let's say 15 is in the middle here and 40 is over here. So as concentrations vary between these two, so starting from 15 all the way to 40, let's take a look at how this enzyme and how this enzyme will function. Well, the green one has a Km of a very small number. So when we start the concentrations of substrates at 15, the green enzyme is going to be super fast because look at how far this concentration is from its Km. There is a lot more substrate than this enzyme needs to work at 50% of its Vmax. So even at 15 micromolar, the green enzyme is going to be working at above 50% of its Vmax. And to be exact on this specific graph, let's take a look where. So let's go up here. Maybe this is 3/4 of Vmax. Okay, so at 15, 3/4, at 40, wow, probably like 90%. Okay, now let's take a look at this enzyme that has a Km of a much higher concentration, 25. So if we're looking at this enzyme at 15 micromolar, the pink one is only going to work at like 1/4 of its Vmax, right? So it's not going to reach at 1/2, whereas at 15, this enzyme reached the 1/2 well, right, and even surpassed it. Now when we get to 40, now this enzyme is going to be past its 40, it's 50%, and maybe be at like 60% or something. Okay, so just this, to answer this question, you just need to describe, and maybe you can draw something like this and show your understanding of this enzyme having a much smaller Km. So when we start concentrations from 15 and up, this green enzyme is already going to be working at more than its 50% of Vmax, whereas this one at 15 micromolar, it is not going to be working at its half Vmax. Okay, so this one will be much, much faster at any given concentration between 50 and 40 micromolar. Okay, and I think that about covers it. Let me know if you have any questions. You can email me. My name is Lilith, or send me a message through Canvas. Or if you have any questions, or if I made a mistake in this video, please let me know of anything that comes up. Okay? All right. Happy studying.